Hi, Chem 101 students. Welcome to the first of two lectures this week. We have a short week because of the Monday holiday, so we're starting on Tuesday this week. The first lecture here will be about light energy. And then as we move forward to the second lecture, we'll be talking about the electron configurations, basically the places in which the electrons are at around the center of the atom, the nucleus. But these two things are quite related, and so that's why they're covered both in the same textbook chapter, which is textbook chapter 8. So that's your reading for this week, the textbook chapter 8. I will say that for the chapter 8.2, I don't go into a lot of the detail that they go into 8.2. I kind of just cover the surface of that one. But everything else I pretty much cover on these lectures, and we'll cover on the quiz. So let's start with lecture 4.1, light energy. We'll talk about light or electromagnetic radiation and how we can describe the light as a wave with a wavelength and a frequency. And we'll also describe how we can talk about pieces of light or particles of light and the energy in each of those pieces or particles. So light can be considered to act like a wave and also like a particle. It's one of those strange things about light and quantum mechanics is that light can move like a wave. It can be accurately described sometimes as a wave, sometimes as a particle. It's kind of both. So when you think of a wave, you probably think of water waves, like waves at the ocean. They go up and down, and light waves do like that too. What's going up and down there though is not water. It's what's called an electromagnetic field, electrical energy and magnetic energy, basically. And this is moving as a wave through space or through, from this light that's above me here to my head, to light this camera, as you see here. So when we talk about a wave, you can think of yourself as like maybe you're on the beach, okay? And you're standing right here. So this is you standing right here on the edge of the beach. I'll make this one black so they can see better against the red line there. And the waves are coming towards you. So the waves are traveling in this direction towards you, and you'll see one wave. It's coming at you, and there's a peak here at the top, and then it hits you and then passes, and then another wave comes. And we can describe one property of wave as the wavelength, which is indicated by this lambda here. It's the distance between the peak of one wave and the peak of the next one. So you might see the next wave coming out as this one's about to hit you. And the distance between these is referred to as wavelength, and it's indicated by this Greek letter lambda. Lambda, and bigger, it looks like that, lambda. Also important to describing the wave is the time it takes between waves to hit you. So if it's a very kind of slow rolling wave, there will be a long time between when the waves hit you. So this is kind of like a slower wave where we have longer wavelengths. Here, if the waves are closer together, then if you're standing right here again, so you're down here at the beach, standing and letting the waves hit you, well, these waves now, assuming that both of these are moving at the same speed, because the waves are closer together, there's going to be a smaller time between the waves. And the time between the waves is referred to as the frequency. So how frequently the waves hit you. It will hit you more frequently if they're closer together. If the wavelength is small, the frequency with which the waves are hitting you would be higher, assuming that the waves are all traveling the same speed, which for light, they generally are. They always are. It's called the speed of light. So electromagnetic radiation can be described as a wave, and the way that you describe this wave mathematically is that the wavelength, this lambda, times the frequency, or how often the wave is passing a certain point, is equal. When you multiply those, you get the speed of light. So c is the speed of light. It's approximately 3 times 10 to the 8th meters per second. So we're talking 300 million meters per second. Light moves very fast. That's why when you turn on the light, you don't notice it right away, or you notice it right away. You don't think that it takes time to hit you, but it does. It just moves very, very quickly. When the distance is very far, like from the sun to the earth, the light traveling from the sun to the earth takes about 8 minutes to get to the earth. And so if the sun were to just disappear right now, it would be 8 minutes before we didn't see any more light getting to us, because that's how long it takes for light to travel from the sun to the earth at the speed of light. And the speed is in meters per second, so that's our unit. Wavelength, the wavelength is generally stated in nanometers for a lot of light, but it can be stated in its base unit is meters. So M, meters, and then the frequency, or how often the wave is passing a certain point, is in units of per second, so waves per second basically, or these are also called hertz is the other name to call 1/seconds. So if you multiply the units here, you have units of meters for the wavelength, and you have units of 1/seconds for the frequency, and so you get for a speed of light units of meters per second, meters over seconds. Now, one thing to note is that if you're standing at the beach here, you can consider the energy that the waves are like hitting you with, right? And it will be more energy hitting you if those waves hit you more frequently. So what we're going to see is that higher frequency corresponds to higher energy of the waves. That's the way you can think about it. Is the waves are hitting you. If the waves are hitting you slowly, one, and then another. That's not hitting you with as much energy or force there. But if they're hitting you over and over and over again really fast, well, then they're going to knock you over, right? They're going to hit you with a lot of energy. Higher frequency will be higher energy. This will be stated mathematically here when we describe light as a particle. So light has this basically weird property according to quantum mechanics that we can describe it as both a particle and a wave. In fact, all matter has this property and energy, but it's very, very noticeable for light because it's all energy, no mass really. So light can be described as a piece as well, not just a wave, but as like a bullet, basically a little BB, right? So it's weird that we can describe it as both of these things, but that's the weird fact of trying to describe nature here, and that's part of quantum mechanics. So the fact that light can be described as both a wave and a particle is called the wave-particle duality of light. So we can describe a single particle of light, which is called a photon, and its energy would be given as this h, which is a constant. That h is called Planck's constant and has a value of 6.626 times 10 to the minus 34 joules times seconds, times this nu here, which is the frequency, and that will give you the energy. And if we're counting out units again and looking at the units, well, we saw that the Planck's constant has units of joules times seconds for the Planck's constant. And for the frequency, we said that the units were 1/seconds here. And so when you multiply those, the seconds cancel, seconds divide by seconds, and you just get joules. And that's the unit for energy. So remember from last week, we talked about energy units, joules. So this shows you with this math, it's explicitly stating if the frequency is higher, then the energy will be higher as well. The bigger this v is, the bigger h time, or this v is actually called a nu. It's a Greek letter nu. It's kind of like a curvy v. And so the bigger the nu is, the bigger the frequency, then the bigger h times the frequency will be, and so the bigger the energy will be. So I'll have you do some math where you calculate between wavelength and frequency, and also calculate the energy of light of a given frequency. So looking back at this, you can see that there's lights of all different colors here. And something we're going to see is that the color of the light, the way we perceive it, it depends on what the wavelength and the frequency of the light are. And so this green light here actually has a wavelength of 550 nanometers about. So the red light is around 750-ish nanometers, a longer wavelength, and the purple light will have a shorter wavelength. So green visible light will have a wavelength of about 550 nanometers, and you don't have to remember what nano means. I didn't tell you you have to remember it. 1 nanometer is 10 to the minus 9 meters. I wouldn't make you memorize that one, but eventually if you take more science, you'll probably have to memorize it. So what is the frequency of green light here? Okay, well, we're given the wavelength. So this is the wavelength right here, which we use this symbol lambda to represent. And we know that the speed of light equals lambda, the wavelength, times nu, the frequency. And what we want to get is the frequency. So we're going to have to solve this equation for frequency. To do that, we should divide both sides by the wavelength. So then our wavelengths cancel, and all we have is frequency here. And so we'll get that the frequency is the speed of light over the wavelength. And the speed of light, you'd always be given that. You don't have to memorize it. It's 3.00 times 10 to the 8th meters per second. And our wavelength was 550 nanometers. So the problem here is that this is not in meters, it's in nanometers. So we're going to want to first convert the 550 nanometers to meters. And so we're going to make sure that we have nanometers on the bottom here so it cancels. And it's 10 to the 9th, or 10 to the minus, what's 10? Oops, nanometers. Oops, I did this wrong. I flipped it. Oh no. Let's get rid of this. So it is, our conversion factor we have here is 1 nanometer. So the number that goes with the nanometer up here is 1. Oops. Erase. Okay. So we have 1 nanometer. So we're going to put the 1 next to the nanometer. And then that is equal to 10 to the minus 9 meters. That's the same as saying 1 times 10 to the minus 9. And so here we put nanometers in the bottom, so our nanometers will cancel and we'll end up with meters. And that's what we need here. Okay, so let's do that in our calculators now. So we're going to do 550 times 1 EE negative 9. And your calculator might give you a very small number, or if you display in scientific notation, we'll display this way, and we get 5.5 with 2 sig figs, because this 5 is the last sig fig, times 10 to the minus, what was it? Times 10 to the minus 7 meters. And so that's what we're going to put in for our wavelength. 5.5 times 10 to the minus 7 meters. And in terms of units, our units on the top are meters, our units on the bottom are meters. Those will cancel. All that's left is, in terms of units, is 1 over seconds. Now we have to divide our here our speed of light over our wavelength, okay, to get our frequency. All right, and we get 3 EE8 divide by 5.5 EE minus 7. 7 negative equals, and we get a frequency of 5.5 times 10 to the 14 1/2 seconds, or we can also call these hertz. And so that is our frequency. Okay, so that's how we can solve between wavelength and frequency. We use this equation to go between wavelength and frequency. What if I was asked, what is the energy of a photon of this green light? To figure out the energy, we use the equation energy equals Planck's constant times the frequency. Planck's constant is given to us. It's 6.626 times 10 to the minus 34 joules times seconds. And you would be given that. You don't have to memorize that number. That's just a constant. It's always the same, just like the speed of light is always 3 times 10 to the 8th c. H is always 6.626 times 10 to the minus 34 joules times seconds. And our frequency is 5.5 times 10 to the 14th 1/seconds. So in terms of units, our units here are seconds on the top, divide by seconds, so those cancel. And all we have left for units is joules, which is what we wanted. So we just have to plug this into our calculator now. 6.626 times 10 to the 34 minus, make sure that's minus, times 5.5 is 10 to the 14. And so our energy, which is very small because it's only for one photon, which is not a lot of light, it's very, very little. Our energy will be 3.6 times 10 to the minus 19 joules. Energy equals 3.6 times 10 to the minus 19 joules. And I also wrote my work over here so you could check later. So that's how you use these equations. It involves, dividing and multiplying numbers that have scientific notation. So kind of what we practice in week 2 a lot. And if you're having trouble with those, you want to practice more. Fortunately, in our experiment this week, we do a little bit more stuff with sig figs and multiplying and dividing. So that should help a little bit. So we just did this calculation for green light. As we said, the green light was about 550 nanometers in terms of wavelength. What we've got here is the figure from your book that shows the electromagnetic spectrum. So this electromagnetic spectrum is set up so that we have higher and higher frequency, or in 1/seconds or hertz, as we go left to right, and smaller and smaller wavelengths. And this is an important point. Frequency and wavelength are inversely proportional to one another. They're given by this equation, and the c is a constant. Okay, so let me show you how these are inversely proportional to each other. Let's say my constant was 6, okay? And my wavelength is 3. Then what has to be my frequency? If my wavelength is 3, then my frequency would have to be 2. Now what if I instead made the wavelength smaller? So now let's say I made the wavelength 2. Well, then the frequency will have to be bigger. It will have to be 3. So you can see that if the wavelength gets smaller, as we did from 3 to 2, the frequency must be bigger because they also always multiply to a constant. Now c is not actually 6, c is 3.00 times 10 to the 8th meters per second. But I wanted to give you some simple numbers to show you that the way this math is set up, what this means is that if one of these numbers gets smaller, like the wavelength, that means the other one is getting bigger. So as we go left to right, we're getting bigger and bigger frequency. The frequency is going up. And when the frequency goes up, the wavelength is going down. Okay, they go opposite to one another. And remember that bigger frequency means bigger energy. Okay, so this is the relationship that you need to know. And the reason why bigger frequency is bigger energy is because the energy is a constant times the frequency. So if the frequency gets bigger, that means this whole side gets bigger, so more energy here. Now, one question that I like to ask a lot is compare the frequencies and the wavelengths and the energies of various types of light. So let's look at the various types of light on this end here. So on this end, we have a low frequency, high wavelength. So for radio waves, the wavelength can be many meters long. Like radio waves, like what carries the signal for your radio stations. The frequency is relatively low compared to other types of light. And so radio has the lowest energy as well. If it has low frequency, that means also it has low energy. So the radio waves are the lowest frequency, lowest energy radiation. This is the kind of thing our Wi-Fi signals, cell phone signals are carried over, radio stations. So we use these waves to transmit communication media for the most part. A little bit higher energy and smaller wavelength than that is microwaves. Then higher energy and smaller wavelength than that is infrared. Infrared is basically what you feel as heat energy. When you're hit with infrared rays, it causes your molecules to vibrate more and move faster, which is basically being a higher temperature. So we feel infrared as heat energy. Higher energy than that and smaller wavelength is visible light. You can see visible light is actually a very small portion of the entire electromagnetic spectrum. It ranges from a little higher than 700 nanometer wavelength down to a little lower than 400 nanometer wavelength. Out of all the light in the electromagnetic spectrum, we as humans can only perceive with our eyeballs a very, very small portion of this light. Some other animals can see infrared and some can see ultraviolet, or there's machines, of course, that we can use to see these as well. But our own physical human eyeballs are not evolved to see those frequencies of light or wavelengths of light. And higher energy than visible is called ultraviolet light. Now the names infrared and ultraviolet come from their place relative to the visible light. So infrared means lower energy than the red light because it has a lower frequency and a longer wavelength. Ultraviolet means higher energy than the violet light. So higher energy, ultra, higher, violet, but it's above violet, and smaller in wavelength. Even higher energy is X-rays. Like when you go to the dentist, they use X-rays to image your teeth or your bones because X-rays pass through skin very easily, but not through bone. And so they can use those to image bones. And then the highest energy is gamma rays. One of the many reasons why space is dangerous is because there's no atmosphere to protect us from the gamma radiation from the sun. And so that can cause cancer. So scientists wear spacesuits when they're out there to help protect them from that and also to keep them pressurized. And also the hulls of spaceships are made in such a way that gamma rays won't penetrate them. So at the high end here, this is where we have the highest frequency, and that's the highest energy. That's also the smallest wavelength. So remember, wavelength and frequency go opposite to one another, but energy and frequency go together. So a kind of question that I like to ask you about the types of light are to rank the following types of light in terms of increasing or decreasing frequency, wavelength, and energy. And so here in terms of the frequency, so the lowest frequency, well, let's look. We have radio, X-ray, and infrared. So the lowest frequency here is the radio waves. This is more to the left, low frequency. And then the next, what were we asking about again? X-rays and infrared. The next is infrared. So infrared is higher frequency than the radio. And then X-rays are higher frequency than those. So it goes in terms of frequency, radio is lower than infrared, and that is lower energy than lower frequency than X-rays. Now wavelength, it goes opposite to that. So wavelength, it is that X-rays here that will have the smallest wavelength. So on this end is the small wavelength. So the X-rays have the smaller wavelength than the infrared, which has a smaller wavelength than the radio. The radio has the longest wavelengths. So it goes opposite to frequency. X-rays have smaller wavelength than infrared, which has a smaller wavelength than radio. And then energy, energy goes with the frequency. So bigger frequency is bigger energy. So it's going to have the same pattern as frequency. Radio has less energy than infrared, which has less energy than X-rays. Okay. And that will do it for our lecture on light and the different types of light. And so go ahead and check out the homework questions on those that I have assigned you, and also make sure to read the book, section 8.1. And then we'll move into the remainder of the chapter. It's 8.1 and 8.2, I think. Yeah, anyway, I have it in the instructions anyway, but the beginning of chapter 8 is where we talk about light. And then we'll begin to talk about the electron configurations in the next lecture.